Hey guys, I want to make a little video. We got to look at different types of graphs. I want to review some of the things we talked about in a previous video, starting with the first law. Delta U equals Q plus W. Delta U is the internal energy of a gas or a system that usually includes a gas, and it's equal to the heat absorbed by a system and the work done on that system. So these two things are positive, then you have a positive change here. If you add Q, if you add heat, or if you have work done on the system, okay, then that's positive. Okay. What does it mean for a system to do work, right? Most of the time, a lot of examples that we see on the AP test involve something called a cylinder with a piston. The piston can move. We can force this gas down, we can compress the gas, or we can have the gas move to force the piston up. This is what happens in our cars when people talk about a 6-cylinder car versus an 8-cylinder car or a 4-cylinder. They're talking about these things. We have these little controlled explosions going on inside of there. That's how our cars move. We talked about PV graphs last time and how the area under the graph tells us the work done, right? Very important. We're going to talk more about these graphs here in a minute. Okay, so this has been very confusing, and it's still confusing, and I'm going to try again. When the gas is compressed, you take a gas and you compress it. You are making the volume smaller. So the final volume is smaller than the initial volume. And your change in volume will be negative. You take a negative volume change and multiply it by the negative P, you will get positive work. You say the work done on the gas is positive. This fits with my prior notes that I had talked about. Here you can see that. In my prior notes, that if we have a negative volume change, so the volume gets smaller, right, then we have positive work. We say the work done on the gas. Work done on the gas will be positive. So there you go. The gas is allowed to expand. Delta V is positive. What does that mean? That means the gas has expanded. It's pushed the piston up. Final volume is larger than the initial volume. So our change in volume is positive. We could say the work done on the gas is negative. Okay. We could also call this work done by the gas. Okay. So here's the problem. The problem is that we have this phrase, work done on the gas by the environment. We could also say work done by the gas on the environment. So it depends on the phrasing and what's going on, whether you have a negative or positive volume change. So here, if the gas expands, the change in volume is positive. When you take a positive volume change and multiply by this negative sign, you get negative work. So we could say that the work done on the gas by the environment is negative. Another way to phrase that would be to say that the the gas did work to the environment, or the work done by the gas on the environment, right? So this fits with my previous notes, yes, because when we allow the gas to expand, we have a positive volume change. Positive volume times negative gives us a negative work. We could call that work done by the gas on the environment. We could also call it work done on the gas by the environment. So whether you're talking about by the gas on the environment or on the gas by the environment, the wording kind of matters. And I try to follow what's going on with the volume change. You'll see that when we do these new notes, and I had this example here where we went in this clockwise, right? you'll see that we're going to get the same things in new notes. And so we can have something called a cycle. A lot of problems will say, well, we'll start at A, we'll go to B, C, D, and they'll ask you what happens. We talked about this in the prior videos, right? If the cycle begins and ends here at A, then the change should be 0. So your delta U should be 0 because you're back to where you started. First law implies that the Q cycle plus so Q plus W equals 0. So the net heat for the whole cycle is always going to be equal to the net work for the cycle, but opposite in sign in this. So if you have a PV graph and it goes clockwise like this, then you'll get a certain result. You should have negative work if you go clockwise. And this is what happens when you have something called a heat engine. And this fits with my prior notes. We said that if the system rotates clockwise, we get a net negative work. And so what this means is that the system does work on the surroundings. Okay, it receives a net amount of heat and does a net amount of work. This is what our cars do. We use explosions within the engine to do work for us. This is what a heat engine does. Refrigerators go the other way. Okay, this is a counterclockwise cycle. We get a net negative area, and so we get a net positive work. This means that the surroundings do work on the system. Okay. And we don't really talk much about refrigeration in this class. Okay. So if the cycle goes clockwise, work is obtained from that engine. If the cycle goes counterclockwise, work must be put in. And that's what a fridge does. I think people think that fridges add coldness to stuff, right? That's what they're doing, is somehow putting cold in. And what fridges really do is they're removing heat. That's what they do. So if it's counterclockwise, we get a positive work. And so that's what we said here. We said if the system is counterclockwise, we get a positive net work. And there you go. So that may give you a curve like this, and I can ask you questions about this curve. I find the area under that curve. What I would do is break it up into two shapes, like a rectangular shape and this triangle. Pressure on the y-axis, volume on the x-axis. I can find the area of the triangle and the area of the rectangle. Add them up. This would be a clockwise cycle. We're going from left to right. So we'll have a negative work, right? As we said, clockwise will give us negative work. Another example here, area under these lines. Remember, if you have a vertical line, there is no area under that curve, so there is no work. So there's only work from here to here, and there's work from here to here. You can break these up into two little, rectangles, add them up. Since we're going, it looks like we are going to be going from right to left. We're going to get a positive work because we're going right to left. So just like in these notes, right? When we went from left to right, we got a negative. We go from up, down, down, up, we get 0 work. Left to right is negative. Right to left will be positive, and up or down is 0 work done. Here's a cute little problem. You got 4 PV graphs, and you're supposed to put them in order from most negative work done to the most positive work done on the system. So most negative to most positive, right? The answer would be B, A, C, B, D. A right here. So if we go left to right, that's negative. Okay. So it looks like A and C are both negative, they go left to right, and then B and D are positive, they go right to left. Of course, we have to look closely at the shapes to make sure that these areas, right, this looks like this is a larger area. Here A is a larger area than C. And then looks like B is bigger than D. Remember, that's asking for most positive, from most negative to most positive. So we're going from most negative, this is the least negative, this is the least positive, to the most positive. And so that's what they want. You know, this total area here is 4. This total area here is just 3. You might have to take a little look to make sure that you understand. Here's a problem. Sketch a PV diagram, find the work done on the gas during the following stages. A gas is expanded from a volume of 1 to a volume of 3 at a constant pressure. So here we go. We're going from 1 to 3. This is our volume down here. The pressure is constant, so it looks like we're going to have a line that goes across, and it will be horizontal. Boom. Work done. Alright, we have a positive volume change, so we're going to get a negative because we have positive volume times negative, so we should get a negative answer. There you go. Volume is 3 minus 1. This is in atmospheres. Yep. And they converted. I'm not that worried about the math. I'm worried about, can you draw the graph? Do you know what's going on? Positive, negative, volume change, that type of thing. Alright, the gas is then cooled at a constant volume until the pressure falls to 2. So our pressure is going to go from 3 to 2. Gas is cooled. Looks like volume will stay constant. Yeah, constant volume. How much work is done? No work. There's no area under that curve. The gas is then compressed at a constant pressure of 2 atmospheres. So we are going to compress it. We're going to go from 3 to 1. So we're going to have a volume change from 3 to 1. Looks like we're going to make a little box. We're going to have a negative volume change. When we take negative and multiply by negative, we should get a positive work. Okay? We are compressing that gas. And then the gas is heated until the pressure goes from 2 back to 3. We're back to where we were. Volume stays constant. So we'll probably have to lock the piston in place to keep the volume constant, and we have no work. Whoop. We have no work done. Net work is area within that little square there. Clockwise. Okay. It's a clockwise cycle. Negative work.